It begins, as so many scientific odysseys do, in the darkness, a darkness not of night, but of understanding. For millennia, humankind drifted through its own dreams without ever glimpsing what machinery stirred behind the eyelids. Sleep itself was an enigma, a small death of consciousness visited upon kings and beggars alike, and dreams, those vivid phantoms that rose within it, were treated as whispers from gods, omens of fate, or messages from the dead. In the dim glow of oil lamps and moonlight, ancient civilizations watched the sleeper's breath rise and fall, and wondered what invisible theater played inside the silent skull. They did not yet know that the drama unfolded on the shimmering stage of the brain itself. In the clay libraries of Mesopotamia, nearly 4,000 years ago, scribes pressed wedge-shaped symbols into damp tablets, recording the earliest surviving catalogs of dreams. The Sumerians believed dreams were direct visitations from divine powers, dispatches from the unseen world. The Epic of Gilgamesh spoke of dreams foretelling heroic quests and cosmic battles, messages interpreted by seers who claimed to speak the language of sleep. Egyptian priests, centuries later, built entire temples for the purpose of dream incubation, where pilgrims lay upon consecrated stones, hoping for visions sent by their gods, their minds drifting under the warm night air of the Nile. Even the pharaohs submitted to these rituals, believing that through dreams they communed with deities and ancestors who ruled over destiny itself. In Greece, the philosophical gaze turned inward. Aristotle, writing in the 4th century BCE, pondered dreams with the same curiosity he brought to stars and insects. To him, dreams were not celestial telegrams, but natural phenomena born of the body, the movements of the soul in sleep. He speculated that dreams arose from sensations lingering in the blood, echoes of the day's perceptions reverberating through the cooling organs of the night. It was a vision both mystical and physiological, a first attempt to translate the spiritual into the natural. Hippocrates, too, considered the sleeper's inner life diagnostic. The content of dreams might reveal the hidden imbalances of the body's humors: yellow bile, black bile, blood and phlegm. In those early medical theories, one can glimpse the faint silhouette of neuroscience, though still veiled in the language of ancient medicine. Through the Roman centuries, dream interpretation remained both art and superstition. Cicero scoffed at the notion of prophetic dreams, while Artemidorus compiled volumes of symbolic lexicons. If you dream of waves, expect turmoil. If of fire, passion or destruction. Dreams became currency in the marketplace of meaning. Yet beneath the allegories, a subtle question endured. What part of the human creature dreams? Is it the soul or something humbler, the organ that beats within the skull? For 2,000 years, that question lay unanswered. The Middle Ages saw theology drown inquiry beneath faith's tide. Dreams were moral parables, instruments of temptation or revelation, depending on whether one's sympathies lay with heaven or hell. Augustine, wrestled with nocturnal visions, fearing their carnal origins. Monks chronicled dreams of saints and martyrs, the unconscious now a battlefield between divine and demonic forces. The sleeping brain, unimagined as yet, slumbered too in the history of science. Then came the Renaissance, and with it light. The anatomists of Padua and Bologna dared to cut open the head, tracing nerves, ventricles, and folds of gray matter. Leonardo da Vinci's notebooks show sketches of skulls sliced open like pomegranates, each sulcus drawn with reverent precision. He speculated that the senses converged in the senso comune, a seat of perception within the brain's chambers, an echo, perhaps, of consciousness itself. The dream, still elusive, hid somewhere within this organ now revealed to be intricate, pulsing, alive. Yet even as Galileo turned his telescope to the heavens, no instrument yet existed to look inward upon the cosmos of sleep. By the 17th and 18th centuries, philosophers like Descartes and Hobbes wrestled anew with the riddle of mind and matter. Descartes' evil demon could deceive him in waking life. How then could he trust his dreams? Hobbes, ever the mechanist, imagined dreams as the echoes of motion within the brain, fading sensory impressions swirling like eddies in a slowing river. Dreams, he proposed, were the remnants of thought persisting after the gates of the senses had closed. It was a poetic intuition of what future neuroscience would confirm, that the dreaming brain replays, recombines, and transforms the fragments of waking experience. Meanwhile, science crept toward sleep itself. Physicians noted patterns. The sleeper's muscles relaxed, breathing slowed, yet sometimes eyes darted beneath closed lids. Nobody knew what this meant. There was no way to peer through bone and darkness. The brain was a fortress without windows. The 19th century cracked that fortress open. Electricity became the key. When Luigi Galvani made frog legs twitch with sparks, he revealed that the body ran on electrical currents. His nephew, Giovanni Aldini, extended the spectacle to human heads, grim experiments that nonetheless hinted at a truth. Thought, movement, even dreaming might be electric. By mid-century, scientists like Émile Dubois-Reymond and Hermann von Helmholtz mapped the speed of nerve conduction, measuring impulses in milliseconds. The brain was no longer a black box of soul. It was a living engine, its parts conducting minute lightning through tangled circuits. The psychology of dreams took a parallel path. In 1899, a Vienna neurologist named Sigmund Freud published The Interpretation of Dreams, a work that would dominate the 20th century's imagination. Freud, trained in the physiology of the nervous system, yet drawn to the murky depths of the psyche, proposed that dreams were disguised fulfillments of repressed wishes. The brain, he thought, was a stage upon which forbidden desires rehearsed themselves under the sensor's dim light. His patient, the wolf man, dreamt of white wolves perched in trees. Freud saw sexual trauma encoded in symbolism. Whether one accepts or rejects Freud's conclusions, his central intuition that the dream world obeys a logic distinct from waking life remains foundational. He shifted the study of dreams from divine prophecy to human psychology, from the heavens to the head. But even Freud could not see the machinery at work. His century would. In 1929, Hans Berger, a quiet German psychiatrist obsessed with telepathy, invented the electroencephalogram, the EEG. Hoping to find proof of mental transmission, he instead discovered the electrical rhythms of the living brain. Thin wires attached to the scalp traced the first visible hieroglyphs of thought, the slow alpha waves of calm, the faster beta waves of alertness. When subjects fell asleep, Berger watched those rhythms change. Large rolling delta waves heralded the descent into deep sleep. The invisible had become visible. For the first time in human history, one could watch sleep unfold. The 1930s and 40s refined the map. Sleep researchers observed that the night was not a continuous descent into oblivion, but a series of cycles, each lasting about 90 minutes, descending from light to deep sleep and rising again. Yet one piece was missing: the storm that raged behind closed eyes. It was not until 1953, in the University of Chicago, that Eugene Aserinsky, a graduate student under Nathaniel Kleitman, noticed the phenomenon that would transform our understanding forever. While monitoring his son's sleep, Aserinsky saw sudden bursts of rapid eye movement on the recording chart. Twitching eyes, irregular breathing, vibrant brain activity, and when he awakened to boy, the child reported dreams in full color and motion. REM sleep had been discovered. The age of dream science had begun. The following decade brought pioneers like William Dement, who mapped the architecture of sleep with the precision of an astronomer charting constellations. Each night, they found, the brain traverses several REM periods, each longer than the last, interspersed with quieter phases of non-REM rest. During REM, the brain's electrical activity resembles wakefulness, yet the body is paralyzed, an exquisite paradox nature devised to prevent us from acting out our dreams. Electrodes placed on sleepers showed bursts of activity in the visual and emotional centers of the brain, while frontal regions, the governors of reason, dimmed. Thus, the dream's landscape of vivid imagery and illogical plot mirrored the brain's own shifting balance of power. By the 1960s, scientists began to probe deeper. Michel Jouvet in Lyon studied cats whose brainstems he partially disabled. When they entered REM sleep, their bodies leapt and prowled as if hunting invisible prey. Jouvet realized that a tiny region in the pons suppressed motor activity during dreams. Disable it, and the dream breaks into the body. He called REM sleep the paradoxical sleep, where the mind is awake but the muscles are frozen. In those same years, Dement and others recorded dream reports immediately after awakenings, correlating brainwave patterns with the narrative intensity of the dreams. They found that the most vivid dreams coincided with REM, but milder, more thought-like mentation appeared in other stages too. Dreaming, it seemed, was not a single switch, but a continuum. The Cold War years gave the study of sleep an institutional home. Laboratories from Stanford to Leningrad, filled with volunteers, wired to electrodes, observed through glass as they slept under fluorescent lights. The EEG hum of the night replaced the hum of engines and bombers, a quieter frontier of human exploration. Scientists sought to quantify everything: eye movements per minute, microvolts of cortical firing, minutes spent in each stage. They discovered that newborns spend half their sleep in REM, perhaps because their brains, still forming, need that internal simulation to organize neural connections. Adults, by contrast, spend less than a quarter of the night in REM, as if the brain, matured, requires fewer rehearsals. Even so, when deprived of REM, subjects became irritable, anxious, disoriented. The brain, deprived of its nocturnal theater, demanded an encore. Psychology, meanwhile, waged its own revolutions. Freud's shadow loomed large, but new theories rose. J. Allen Hobson and Robert McCarley proposed in the 1970s the activation-synthesis hypothesis. They argued that dreams arise from random bursts of activity from the brainstem during REM. The higher brain then weaves these signals into coherent, though often bizarre, narratives. Dreams, in this view, were not cryptic messages from the unconscious, but the cortex's attempt to make sense of physiological noise, like a storyteller improvising meaning from scattered cues. The hypothesis was revolutionary, dethroning Freud's symbolist empire with neurobiology's mechanistic rigor. Yet it did not explain everything. Why, if dreams were random, did they so often echo our emotions, fears, or memories? Why did nightmares return after trauma, or creativity flourish in dreams? The mystery deepened. Advances in neuroimaging from the late 20th century would begin to answer these questions. Positron emission tomography, PET, allowed scientists to observe which regions of the brain consumed energy during sleep. They found that in REM, limbic structures, the amygdala, hippocampus, anterior cingulate, flared with activity, while the dorsolateral prefrontal cortex, seat of rational judgment, dimmed. Emotion surged as reason slept. Visual areas, too, glowed with internal light, explaining the richness of dream imagery. It proposed a universal grammar of dreams, emotion, basic language. Fear is pursuit, joy is flight, pleasure is nurturance. It was here that modern neuroscience began to glimpse the secret architecture of the dreaming mind. By the 1990s, sleep research converged with cognitive science. Dreams were no longer studied solely for their content, but as windows into consciousness itself. What does it mean that the brain can simulate reality so convincingly that we believe it, only to awaken and find it gone. The question fascinated philosophers and computer scientists alike. Some liken dreams to virtual reality, the brain as its own simulator, testing predictions in the safety of darkness. Others proposed evolutionary functions, that dreams served as rehearsals for threats, a theory advanced by Antti Revonsu in Finland, who argued that ancestral humans who practiced danger in dreams may have survived better when danger came. Nightmares in this light were not punishments, but training.
Neurochemistry added another layer. During REM, levels of serotonin and norepinephrine, chemicals of vigilance, drop, while acetylcholine rises, promoting vivid internal imagery. This chemical cocktail may explain why dreams feel so real, yet elude memory. The neurotransmitters that encode long-term memory are dialed down. We live entire dramas each night, only to lose them upon waking, because the brain, by design, forbids the storage of its nocturnal hallucinations. Still, fragments slip through, the residue of a larger symphony played behind the curtain. Sleep itself, long considered a passive state, emerged as one of the most dynamic behaviors in biology. During slow-wave sleep, the deepest stage, the brain replays patterns of neural activity from waking life. Rats that ran mazes in the day exhibit the same firing sequences in their hippocampi during sleep, as if reliving their paths. Humans show similar reactivation during memory tasks. The dreaming brain, it turned out, was not idle, but editing, sorting, strengthening. Sleep spindles, bursts of rhythmic activity, appeared to mark the transfer of memories from temporary storage in the hippocampus to the vast archive of the cortex. Dreaming might be the conscious shadow of that unconscious consolidation, the narrative our mind weaves as it files away experience. As the 21st century dawned, imaging technologies grew finer still. Functional MRI allowed researchers to watch blood flow across the brain's networks in near real time. When subjects were awakened from REM and asked to describe their dreams, scientists matched their reports to the activation patterns just recorded. Visual dreams corresponded with occipital activity, auditory ones with temporal lobe engagement, emotional dreams with limbic surges. The correspondence was so consistent that some labs began to reverse engineer the process, decoding dream content from brain activity alone. In Japan, Yukiyasu Kamitani's team trained algorithms on fMRI data of waking subjects looking at images, then applied those patterns to sleeping brains. Astonishingly, the AI predicted categories of dream content, animals, buildings, faces, with above-chance accuracy. It was the first tentative step toward reading dreams, though the inner narrative remained safely encrypted. Meanwhile, Clinical research illuminated how dreaming intertwines with mental health. PTSD sufferers often relive trauma in recurring nightmares. Their REM sleep shows heightened amygdala activity and disrupted frontal modulation. Therapies like imagery rehearsal training, consciously rewriting the nightmare's ending while awake, can reshape the dream itself, hinting at the brain's plasticity even in sleep. Depression, too, alters REM patterns. Patients often enter REM faster and stay longer, as if trapped in emotional rehearsal. Antidepressants, which modify serotonin and norepinephrine levels, reduce REM intensity, perhaps explaining their influence on mood. The sleeping brain, it seems, mirrors the waking one's emotional state, a nightly reflection of mental equilibrium.
Yet despite these advances, much remains tantalizingly out of reach. Scientists can trace waves and regions, neurotransmitters and cycles, but the subjective essence of dreaming, the felt reality, the shifting self who experiences it, resists full capture. Some researchers propose that dreaming is a form of offline consciousness, generated when the brain, cut off from sensory input, turns inward to model possibilities. Others see it as a kind of mental housekeeping, integrating memories into coherent stories to maintain the sense of self. Still others suspect dreams serve no single purpose at all, mere byproducts of a brain too creative to rest. But to stand at the threshold of sleep, knowing that within moments your consciousness will dissolve into visions only your own neurons can produce, is to feel that ancient awe the Sumerians felt under their desert stars. In recent years, the boundary between waking and dreaming has grown porous through the study of lucid dreaming, the rare state in which the dreamer becomes aware of dreaming without awakening. Researchers like Stephen LaBerge taught volunteers to signal from within dreams by moving their eyes in predetermined patterns detectable on EEG. These experiments proved that self-awareness could indeed exist inside a dream, and that the dreamer could influence the narrative. Lucid dreaming opened the door to exploring consciousness itself as a manipulatable variable. Inside REM, with sensory gates closed and imagination unbound, the mind could learn to recognize its own creation, a laboratory of the self. Neuroscientists found that lucid dreamers showed activation in the prefrontal cortex, reawakening of regions usually dormant during ordinary REM. Awareness, it seemed, could be reintroduced into the dream like a light switched on in a darkened theater. And with that light, a new era began, one where sleep was no longer the border of science, but its new continent, stretching vast and mysterious beneath the eyelids of humanity. The phenomenon of lucid dreaming inspired a new generation of explorers to treat the night as a field of experimentation. In the 1980s and 1990s, LaBerge's team at Stanford constructed elaborate setups where dreamers, trained in awareness techniques, entered REM and signaled recognition through precise left-right eye movements recorded by electrodes. From that moment on, the wall between the conscious and unconscious began to crumble. Subjects were instructed to fly, to speak, to write within their dreams, and their physiological markers changed accordingly. Pulse and respiration quickened when they exerted effort, as though imagination alone could command flesh. The brain had proven capable of creating a reality so convincing that even within it, one's body responded as if it were true. Across the Atlantic, in Germany, Ursula Voss and colleagues later confirmed with EEG that lucid dreaming reactivates the frontal cortex, restoring metacognition, the ability to know that one knows. The dreamer becomes a self-aware narrator, a scientist within their own neural experiment. For philosophers of mind, this discovery carried enormous implications. Consciousness, long treated as a binary, on when awake, off when asleep, now revealed itself as a spectrum, capable of shades, of layered awakenings. Within this new gradient, sleep was not unconsciousness, but a different mode of being conscious, one unmoored from the external world.
As these experiments matured, another revolution was unfolding in parallel: the decoding of sleep architecture at the molecular level. The same decade that witnessed the birth of lucid dream research also saw the identification of REM-specific neurotransmitter pathways. In the brainstem, clusters of neurons in the pons and midbrain release acetylcholine to ignite cortical activation, while neighboring cells suppress monoamines like serotonin and norepinephrine. This neurochemical seesaw orchestrates the nightly alternation between slow-wave sleep and the storm of REM. The precise timing of these oscillations, governed by circadian genes such as PER and CLOK, links the drama of dreams to the planet's own rotation, making every vision a small echo of Earth's turning. Meanwhile, outside laboratories, culture responded to these discoveries with the excitement once reserved for astronomy. Dreaming was no longer a private mystery. It was a shared biological heritage, its mechanics available to investigation, its patterns measurable. In popular imagination, sleep scientists became explorers of an inner cosmos. Films like Inception borrowed their vocabulary. Art installations pulsed to the rhythm of recorded brainwaves. Even advertisements invoked REM as a promise of creativity. The public learned new words: circadian rhythm, delta wave, hypnagogic state, and the boundary between science and poetics blurred once more, as it had in Aristotle's time. Yet, in the sterile hum of sleep laboratories, another question grew louder. What happens when dreaming fails? Neurologists began to study patients with lesions in specific brain regions, and from their losses, they reconstructed the dream's machinery. Damage to the temporoparietal junction often silenced dreams entirely, a condition called Charcot-Wilbrandt syndrome. Others with occipital injuries lost visual imagery but retained abstract thought, dreaming in concepts rather than pictures. These natural experiments revealed that dreaming was not an indivisible phenomenon but a symphony of specialized instruments: vision, emotion, narrative, self-awareness. Remove one, and the music changes. The field of cognitive neuroscience seized upon these cases to test competing theories. Was dreaming a mere byproduct of REM, or could it arise independently? Studies of patients with brainstem damage, unable to enter normal REM, showed that some still reported dreams, though fainter and fragmented. Dreaming, therefore, was not tied exclusively to REM physiology, but could emerge from distributed cortical networks. This insight shattered decades of orthodoxy. The dream was not a stage limited to one act of sleep, but a motif that played throughout the night, modulated by depth and chemistry. At the same time, sleep research intersected with the rising tide of computational neuroscience. In the 2000s, models of the brain as a predictive machine, constantly generating hypotheses about sensory input, transformed how scientists thought about perception itself. According to this predictive processing view, the brain never passively receives information. It predicts and corrects, constructing reality from within. Dreams, under this light, became the ultimate proof. When external input ceases, the predictive engine continues unrestrained, generating an entire world from the top down. Each night, the brain rehearses its core function, constructing reality, but now with no tether to the senses. The dream thus becomes the mind's purest simulation, a virtual world rendered by neurobiology long before computers could imitate it.
Experiments supported this model. When researchers monitored the sleeping brain, they found that the same hierarchical networks used for perception, from the primary visual cortex up through the temporal and parietal association areas, remain active in dreams, firing as though real light and sound were entering the senses. The difference lies in feedback. During REM, external signals are gated off by thalamic filters, leaving the cortex to feed upon itself. The result is a self-sustaining loop of prediction without correction, imagination mistaken for reality. This elegant architecture explains both the vividness and the strangeness of dreams. They feel real because the same neural machinery constructs them, yet they drift into absurdity because no sensory truth reins them in. Meanwhile, long-term studies of sleep deprivation exposed how vital these nightly processes are. When volunteers were kept awake for days, their cognition fractured, memory declined, emotions surged uncontrollably, hallucinations crept in at the edges. In rats, total sleep deprivation led to death within weeks, despite adequate food and water. The precise cause remains debated: immune failure, metabolic collapse, or neural toxicity. But the message was clear: sleep is not optional. Within that necessity lies dreaming, perhaps as integral as breathing. The brain demands its cycles of rest and simulation to maintain coherence, pruning synapses, recalibrating circuits, preparing for another day in reality's theater. By the early 21st century, neuroscientists were speaking confidently of sleep-dependent plasticity. Studies using two-photon microscopy showed that after animals learned new tasks, dendritic spines, the tiny protrusions that connect neurons, sprouted and stabilized during sleep. In humans, memory tests confirmed that performance improved after a night's rest, especially when REM followed slow-wave sleep. Dreams, then, might represent the conscious echo of this reorganization, the subjective film of a molecular process. Each bizarre narrative, each impossible transformation may reflect the brain's effort to weave yesterday's fragments into tomorrow's knowledge. Yet dreams are not solely cognitive machines, they are emotional theaters. Brain imaging consistently reveals the amygdala, the almond-shaped seat of fear and passion, blazing during REM. Some researchers interpret this as overnight therapy. By replaying emotional experiences in a context free of physical consequence, the brain may desensitize itself, softening trauma, rehearsing coping strategies. Others see it as creativity unbound, the amygdala's energy fueling associative leaps impossible in waking logic. It is perhaps no coincidence that artists, from Coleridge to Dali, mined their dreams for inspiration, claiming that visions born of sleep carried a logic deeper than reason. Even modern technology has tried to harness this. Devices now exist that play subtle auditory cues during REM to nudge dream content, a scent, a sound, a phrase. Experiments show modest success. Sleepers exposed to the smell of roses dream pleasant scenes. Those exposed to smoke report anxiety. It seems the sealed vault of dreaming can be whispered into, though never fully controlled. Startups promise to train lucid dreaming through wearable headbands. Militaries quietly study sleep for performance enhancement. Therapists explore dream modulation for PTSD. The ancient desire to influence the messages of sleep has returned, now armed with electrodes instead of incantations.
Meanwhile, the brain itself continues to reveal its nocturnal choreography. Recent magnetoencephalography (MEG) studies capture millisecond-level dynamics, showing that during REM, the default mode network, regions linked to introspection and memory, synchronizes with the salience network, responsible for detecting importance. This coupling may underlie the dream's narrative coherence, its tendency to transform mundane memories into emotionally charged stories. When these networks fall out of sync, as in certain psychiatric conditions, dreams become fragmented, echoing the disorganization of waking thought. Thus, the study of dreams becomes a mirror for the study of mental illness, each reflecting the other's architecture. In Alzheimer's disease, for instance, REM sleep diminishes years before cognitive symptoms appear, suggesting that the nightly maintenance of neural circuits breaks down early in degeneration. In Parkinson's REM behavior disorder, the loss of paralysis during dreams can precede motor symptoms by decades, offering a predictive biomarker. Sleep, once considered the opposite of life's activity, now stands as its sentinel, revealing pathologies long before consciousness notices. As the scientific world absorbed these revelations, historians of medicine began tracing the lineage of dream study with new appreciation. They saw continuity where once there seemed rupture. The oracles of Mesopotamia and the MRI machines of modern labs, though separated by millennia, shared the same impulse: to find meaning in the unseen movements of the night. The difference lay not in curiosity, but in method. Where the ancients sought divine messages, modern scientists seek neural codes. Yet both confront the same mystery:
how a person can lie motionless and yet traverse landscapes, feel terror, joy, and love, all within the theater of the skull. In 2013, researchers at the Max Planck Institute captured a remarkable event: a lucid dreamer performing prearranged tasks inside a dream while their brain activity was measured by fMRI. When the dreamer clenched their imagined fist, the motor cortex activated exactly as during real movement. The border between thought and action dissolved. Consciousness, it appeared, could simulate embodiment down to the neuronal level. Philosophers of embodiment seized upon the finding. If dreaming can reproduce the sensory and motor patterns of waking life, perhaps reality itself is but the brain's most consistent dream. Such speculations, far from idle, feed into artificial intelligence research. Neural networks trained on vast data sets mirror the brain's predictive algorithms, learning through replay, a process strikingly similar to REM consolidation. Engineers explicitly model dream phases, allowing machines to reinforce patterns offline. The brain, it seems, invented the principle billions of years before silicon called up. In this sense, every line of code inspired by the sleeping mind is part of humanity's oldest technology, the simulation of experience.
Yet, even as algorithms mimic dreaming, the subjective heart of the phenomenon resists digitization. Scientists can map activation, record pulses, predict categories, but they cannot step inside another's dream. Each mind remains a solitary cinema, its reels unshareable. This solitude, some argue, preserves the dignity of consciousness. There are places science may measure, but never inhabit. And yet, research presses on, driven by the same hunger that once built temples to Somnus, god of sleep. The hope is not voyeurism, but understanding, to know why the brain must weave stories when the world grows silent. Neuroanthropology adds still deeper context. Across cultures, dream practices shape identity. In the Amazon, the Oktuar people share dreams each dawn, interpreting them as guides for daily decisions. Among Australian Aboriginal groups, the dreaming constitutes a cosmological origin, the timeless realm where ancestors sang the world into being. Anthropologists find that such traditions engage the same neural machinery of imagery and emotion that modern science describes. What differs is interpretation. For them, dreams are social and sacred. For us, electrical and chemical. But both stem from the same biological imperative to render experience into meaning. Thus, the history of dreaming is also the history of humanity's search for order amid chaos.
In the 21st century's second decade, computational neuroscience made another leap. The ability to reconstruct coarse visual imagery from brain activity. Volunteers viewed thousands of images while fMRI recorded patterns. Algorithms learned correlations between voxel activations and visual features. When the subjects later dreamed, the same algorithms guessed, with uncanny success, the general category of what they saw. An animal, a person, a building. It was not mind-reading in the mystical sense, but it proved that dreams obey statistical regularities, physical signatures carved in blood and oxygen. What was once the province of prophets now belonged to pattern recognition. At the same time, scientists revisited an older question: do animals dream? The answer, gathered from decades of ethological and electrophysiological studies, is almost certainly yes. Cats twitch and vocalize in REM. Rats' hippocampal neurons replay mazes. Birds rehearse songs in their sleep. In one elegant experiment, zebra finches learned melodies. During sleep, their neural patterns mirrored those of singing, as if practicing silently. Dreams, it seems, are as ancient as vertebrate memory itself, a feature, not a bug, of evolution's design. The sleeping brain rehearses survival, whether predator or prey, human or sparrow. To dream is to prepare, to simulate a world before waking meets it. As for humans, the modern landscape of dreaming grows ever more intricate. Sleep trackers log nightly cycles with consumer precision. Millions of data points reveal population-level trends. Researchers find that city dwellers dream shorter, more fragmented dreams than rural counterparts. That screen exposure delays REM onset. That global crises alter collective dream themes. The COVID-19 pandemic triggered a wave of vivid, anxiety-laden dreams, a dream surge documented across continents. The brain, confined by lockdown, expanded its inner theater, processing uncertainty through metaphor. Historians may one day read that archive of dreams as cultural fossils of a global event.
Meanwhile, neuroscientists probe even deeper into the biochemistry of sleep's architecture. They trace the oscillations of calcium in glial cells, the ebb and flow of cerebrospinal fluid washing toxins from neural tissue, the brain's nightly cleansing. During slow-wave sleep, the glymphatic system opens channels between cells, flushing metabolic waste. Some speculate the dreams may accompany this washing, the mind's stories flowing alongside its fluids. The poetry of that image is not lost on scientists. Thought and waste, memory, and matter, all recycled in the dark. By now, the study of dreaming stands at the crossroads of every major science: biology, psychology, physics, computation, philosophy. Each discipline contributes a fragment, yet the whole remains elusive. Perhaps that elusivity is intrinsic. Dreams are not things to be captured, but processes like weather in the brain. They rise, swirl, dissipate. To describe them fully would require describing the self that dreams, and that, so far, remains the deepest mystery of all. But the journey through history continues, winding back to the laboratories where electrodes glow in the dim blue light of monitors, where sleepers lie encased in wires like astronauts preparing for launch. Outside, night covers the world, but inside, the scientists watch the flicker of electrical storms. Every spike, every ripple, every eye movement is a clue, a footprint of consciousness crossing into its other form. And as these watchers lean over the data, they echo the ancient priests who once leaned over dream tablets in tracing divine patterns. The tools have changed, the wonder has not. In the dim corridors of modern research centers, where the rhythmic buzz of EEG machines replaces the chant of oracles, a new generation of scientists chase what philosophers once called the soul's shadow. The sleeper becomes a cartographer of inner continents, and every spike of voltage marks the passage of some invisible traveler across the terrain of the mind. It is midnight in a lab at Lausanne or Kyoto, and the body in the bed lies utterly still. Yet, on the monitors, the brain blooms with activity. Patterns emerge and dissolve like constellations, sharp bursts of theta waves, slow undulations of delta, the delicate tremor of REM fluttering through the temporal lobes. Researchers, peering into this nocturnal sea, realize that they are watching thought itself drift free of the waking world. What they discover next reshapes the very definition of sleep. During REM, the neurons of the cortex fire in dense synchrony, as though conversing in a language of light. This conversation follows no external script. Sensory input is shut out, muscles paralyzed, the body adrift in biochemical suspension. Yet the brain behaves as if fully awake, its metabolic rate nearly identical to daytime. It consumes oxygen greedily, especially in the visual cortex and limbic regions, while the rational prefrontal lobes rest. The resulting imbalance gives rise to that peculiar logic of dreams, vivid yet irrational, passionate yet ungoverned. Modern imaging renders these shifts visible. Color-coded maps of blood flow, where red marks emotion, blue reason, and gold the electric pulse of imagination. To gaze upon them is to see what the ancients only sensed, that dreams are not chaos, but the structured work of the living brain, pursuing its nightly craft.
And yet, even as this knowledge accumulates, the deeper enigma persists. What purpose could justify such expenditure? Evolution,
parsimonious in its designs, seldom maintains a costly behavior without reason. The brain devotes nearly a quarter of its nightly cycles to REM, a phase incompatible with physical vigilance. Animals that dream are vulnerable, defenseless, easy prey. Why then does nature insist upon it? One school argues for memory consolidation. Here, the hippocampus, our archivist of experience, plays back the day's recordings, compressing them into long-term storage. Neurons that fired together during learning refire in sleep, engraving patterns across cortical tissue. Experiments in rodents show that when such replay is disrupted, memories decay. When it proceeds undisturbed, learning improves. Dreams, in this view, are the conscious echo of that rehearsal, a byproduct of the hippocampus tutoring the cortex. Another school imagines dreams as emotions forge. During REM, the amygdala and anterior cingulate hum with activity, while the stress chemicals of wakefulness, norepinephrine, cortisol, ebb away. Emotional memories reappear, but softened, stripped of their physiological sting. This may explain why nightmares, though terrifying, often fade into catharsis. The mind re-experiences fear in a safe theater, rewriting the script until it no longer burns. Studies of trauma survivors support this. Those who regain healthy REM patterns report fewer intrusive memories. The dream, it seems, may be the brain's most ancient form of therapy. There are other theories still, each unfolding like tributaries of the same dark river. Francis Crick, co-discoverer of DNA, once proposed that dreaming serves to unlearn, to erase spurious connections and clear cognitive clutter. Others describe it as problem-solving in disguise. Kekulé, who dreamed of a serpent biting its tail and awoke with the structure of benzene. Elias Howe, whose nightmare of spears inspired the sewing machine needle. Paul McCartney, who claimed yesterday came to him in sleep. All testify to the creative ferment of the dreaming mind. Neuroscience lends credence. In REM, the brain's associative networks loosen, allowing distant concepts to intertwine. It is a fertile chaos where the improbable becomes plausible and invention takes its first breath. Beyond humans, the evolutionary panorama widens. Every warm-blooded creature studied so far, from opossums to dolphins, shows REM or its analog. Even reptiles once thought dreamless display cycles of brain activity resembling primitive REM. Birds, whose ancestors diverged from ours 200 million years ago, twitch their eyes and wings in sleep as if replaying flight. In cuttlefish, chromatophores pulse through color sequences while the animal lies still, a silent cinema of camouflage rehearsals. It is as though the act of dreaming, or something akin to it, predates mammals themselves, an inheritance from deep evolutionary time. The dream may be as old as complex life's need to remember.
Meanwhile, the boundary between night and day continues to blur under the scrutiny of science. Psychologists studying microdreams and hypnagogic imagery, those flickering visions just as one drifts to sleep, find that they share neural signatures with REM. These fragments, half dream, half thought, reveal the transition of the brain from external to internal control. The thalamus, gatekeeper of sensation, begins closing its portals. The cortex, deprived of input, starts to generate its own. For a few seconds, waking reality and imagination coexist, producing flashes of surreal lucidity. It is here, in this liminal zone, that creativity often sparks, the poet's line emerging from the edge of sleep, the inventor's image caught between consciousness and oblivion. The exploration of this frontier brings neuroscientists face to face with philosophers. If dreams can simulate the sensory world so completely, what distinguishes waking life from illusion? Descartes once doubted his evidence of his senses, suspecting that life itself might be a dream. Today, brain scans vindicate his unease. The neural code for seeing a tree and imagining one overlaps almost entirely. Perception, then, is controlled hallucination, and dreams are hallucination freed from control. The brain's task in both cases is identical: to maintain a coherent narrative of self within a shifting environment. Whether that environment is external or internal matters less than we might think. As understanding deepens, the language of sleep becomes more precise. Scientists now describe the architecture of a night's rest as cycles of N1, N2, N3, and REM, each with characteristic brain rhythms. In N3, or slow wave sleep, neurons fire in massive synchronous waves, a chorus of silence and explosion, repeated once per second. It is during these waves that growth hormone peaks, immune functions reset, and the body repairs itself. REM follows like a counterpoint, the mind's turn after the body's work. The alternation continues 4 or 5 times each night, a biological rhythm as ancient as heartbeat. From these oscillations emerges the unity of human life: waking and dreaming, work and rest, action and reflection, each feeding the other in endless reciprocity. And yet, even with these maps in hand, vast territories remain uncharted. The neurochemical transitions between stages, the role of glial cells in modulating sleep pressure, the synchronization of cortical columns across hemispheres, all these are active frontiers. Recent discoveries of local sleep, where parts of the brain rest while others remain alert, challenge the very definition of being asleep. Dolphins and some birds can shut down one hemisphere at a time, keeping half their brain awake to breathe or watch for predators. Human studies hint at similar micro-patterns. The right hemisphere of insomniacs shows more wake-like activity, perhaps explaining their restless nights. Even within a single skull, consciousness may fragment into regions, some dreaming, others vigilant, a mosaic of awareness shifting through the dark.
From these subtleties arises a profound idea that dreaming might not be an occasional event, but a constant undercurrent of mind, visible only when attention turns inward. Psychoanalysts once spoke of daydreams. Neuroscientists now identify the default mode network, active whenever the mind wanders. The same circuits that generate spontaneous thoughts by day ignite the immersive worlds of REM by night. Dreaming, then, is not a separate faculty, but the mind's native mode of simulation, momentarily constrained by daylight. The difference is one of intensity, not essence. To live is to dream with open eyes. The social sciences, too, have entered this arena. Anthropologists track how societies construct collective meanings around dreams. Historians trace how industrial schedules disrupted natural sleep patterns. Before artificial light, humans slept in 2 shifts, first sleep and second sleep, divided by an hour or 2 of wakefulness around midnight. Diaries from early modern Europe describe families rising to pray, talk, or reflect before returning to bed. During this interval, dreams were shared, analyzed, or acted upon. Only with the advent of gas lamps and clocks did continuous 8-hour sleep become standard. Modern life compressed the night into efficiency, banishing its interlude of contemplation. Perhaps, some speculate, our impoverished dream life is the hidden cost of progress. Yet technology, having diminished sleep, now seeks to reclaim it. Digital therapeutics monitor brain waves and adapt soundscapes to deepen slow-wave sleep. Wearable devices detect REM onset and cue lucid awareness through gentle vibrations. Even the International Space Station runs sleep studies to counteract circadian drift in orbit. For astronauts floating between day and night every 90 minutes, maintaining dream cycles is essential to mental stability. The cosmos itself has become an extension of the sleep lab, proving that wherever consciousness travels, it carries its nocturnal rhythms. Back on Earth, geneticists probe the molecular roots of those rhythms. Mutations in the DEC2 gene produce short sleepers who thrive on 4 hours a night, their clocks running faster than the norm. Others with mutations in PER3 struggle with delayed sleep phase, trapped in permanent jet lag. Each discovery ties subjective experience to molecular timepieces ticking in nearly every cell. Dreams, thus, are bound to DNA, to the spinning of molecular gears that mark the hours of flesh. The ancient question, what governs the seasons of sleep, finds its answer not in astrology, but in the clockwork hidden inside each neuron. Meanwhile, psychiatrists return to dreaming as diagnostic tool. The fragmentation of REM correlates with mood disorders. Nightmares precede psychotic breaks. Yet therapy can also reach through dreams. Lucid dream training reduces recurrent terrors, and guided imagery re-scripts trauma. In clinical rooms lit by soft lamps, patients describe their nocturnal journeys, while electrodes on their scalps translate emotion into waves of signals and patterns. The dialogue between psyche and neuron becomes literal. Freud's couch merges with the modern lab bench. The language of desire meets the grammar of spikes and synapses.
The two great traditions, interpretation and measurement, once rivals, now speak across a shared boundary. All the while, philosophy circles back to its oldest concern, the self that dreams. Experiments show that in dreams, the sense of agency persists even when logic dissolves. One recognizes oneself as a hero or victim, observer or participant. The temporoparietal junction, responsible for body awareness, remains active, anchoring identity amid shifting scenes. When this region misfires, as in certain lucid dreams or near-death experiences, dreamers report floating outside their bodies. The brain thus constructs not only the world, but the I who walks through it. Each night, it rebuilds the self from memory and expectation, rehearsing existence before morning's curtain rises. And still the story advances. In cutting-edge labs, researchers implant optogenetic switches into mice, allowing them to activate specific neurons with light. When they stimulate cells linked to a fearful memory during sleep, the animal's behavior changes upon waking. It avoids places associated with the dream. Here, the line between dream and conditioning blurs. Memory editing, once fantasy, becomes a technical possibility. Ethical questions surge forth. If we can alter dreams, can we alter identity? Can trauma be erased, creativity enhanced, or morality reshaped by sculpting the sleeping brain? The future of dream science, like all frontiers, carries both promise and peril. But for now, the pursuit continues in quieter ways. The gentle whir of MRI coils, the flicker of graphs on monitors, the breath of volunteers beneath blankets of electrodes. Each subject drifts into the same universal darkness that swallowed pharaohs and poets, monks and astronauts. In that darkness, neurons ignite like stars, tracing the same constellations humanity has always followed, the pathways of memory, emotion, desire, and fear. The dream endures as our oldest companion, its language older than speech, its theater older than history. And the scientists, watching from their illuminated rooms, know that every discovery only deepens the mystery. Every answer opens another night. It is late in the 21st century's third decade, and the hum of machines surrounding the sleeper has grown subtler, more precise. Electrodes no longer require thick paste or tangled cords. Tiny sensors rest like flakes of snow along the scalp, transmitting signals through air. The scientist at the console no longer reads wavering lines on paper, but observes living models rendered in shifting three-dimensional holograms. Within those translucent domes of light, waves of color ripple across a simulated cortex, each hue representing an oscillation, each pulse a flicker of neuronal exchange. The experiment unfolding tonight resembles an orchestra playing in silence. No sound, only movement and meaning, every crescendo of electrical energy tracing the symphony of a dream. The subject stirs, eyelids flutter, heart rate quickens. The screen reveals bursts of gamma frequency activity in the visual cortex, a sign that the dream is unfolding in vivid imagery. In the amygdala, red blooms of intensity suggest emotion, perhaps joy, perhaps fear. In the hippocampus, patterns mirror those of earlier in the day, when the same subject explored a virtual maze designed to test spatial memory. The machine, impartial and luminous, watches as yesterday's experiences are replayed, rearranged, dramatized. What the ancient mystics called prophecy, neuroscience now calls reactivation. Yet even with all this clarity, the researchers cannot see the story. They can only infer its existence from these waves. Behind the physiological performance, the dream remains private, untranslatable, sovereign. Outside the lab, night spreads across the planet. In the high deserts of Chile, astronomers observe galaxies billions of light years away. In urban apartments, insomniacs scroll through endless blue screens, their circadian rhythms fractured by artificial light. Humanity's collective sleep has never been more studied, nor more disrupted. Data from wearable trackers, millions of nights condensed into algorithms, reveal patterns of deprivation unprecedented in history. Shift work, anxiety, and the glow of devices push the onset of sleep deeper into the morning hours, truncating REM cycles. The implications ripple outward. Creativity dulls, mood disorders rise, accidents multiply. The planet itself, some scientists remark, has developed insomnia. To understand dreams today is not only to explore the mind, but to diagnose civilization. Governments and corporations, belatedly aware of sleep's economic value, invest in solutions. National institutes fund chronobiology programs. Silicon Valley markets sleep optimization as productivity. The paradox is complete. The very systems that fragmented rest now seek to commodify its restoration. Yet within this paradox lies opportunity. Studies conducted across continents demonstrate that even brief naps rich in REM restore learning capacity, sharpen decision-making, and reduce emotional volatility. The dream, compressed into minutes, performs its quiet alchemy, reweaving the torn fabric of cognition. The more we measure it, the more indispensable it becomes. Meanwhile, deep inside the human skull, the chemistry of dreaming reveals another layer of artistry. During REM, dopamine surges through mesolimbic pathways, the same circuits that govern reward and motivation. This flood may explain the heightened emotion of dreams, their sense of urgency and narrative drive. The sleeper becomes both playwright and audience, drawn irresistibly into plots they never consciously designed. At the same time, The suppression of serotonin and norepinephrine removes the brakes of self-criticism, allowing wild associations to flourish. The dream is thus a laboratory of unfiltered creativity, a biochemical democracy where every thought, no matter how absurd, may rise to power. Upon waking, most of these ephemeral governments collapse, leaving only a few vivid fragments behind, clues from a vanished state. Across the world, psychologists test new frontiers in dream communication. In 2021, an international team achieved what once seemed impossible: real-time dialogue with lucid dreamers. Subjects trained to recognize they were dreaming answered questions from experimenters using pre-arranged eye movements, performing basic arithmetic within their dreams. This interactive dreaming revealed that the mind in REM is not entirely sealed off. Information can flow across the threshold. The implications are immense. Could therapy one day occur inside dreams? Could learning continue while we sleep? The boundaries between consciousness and unconsciousness, once thought absolute, now appear negotiable, like borders between friendly nations.
Yet, as technology advances, ethical shadows lengthen. Who owns the content of a dream recorded by an algorithm? Could targeted advertising invade the sanctity of the sleeping mind, as some futurists warn? The notion seems dystopian, yet faint precedents exist. A beverage company once proposed embedding auditory cues into streaming audio, designed to influence dreams of thirst and refreshment. Scientists protested, invoking a new principle: cognitive liberty, the right to mental privacy even in sleep. For the first time, the frontier of dreaming demands legislation. Humanity, having mapped continents and genomes, now seeks to protect the last wilderness, the uncharted interior night. In the quieter corners of research, others return to biology's fundamentals. At the University of Wisconsin, Giulio Tononi and Chiara Cirelli explore the synaptic homeostasis hypothesis, that sleep, and perhaps dreams, serve to downscale synaptic strength built up during wakefulness. Every experience of the day strengthens connections between neurons. Without pruning, the brain would saturate, overwhelmed by its own learning. Sleep, by reducing the amplitude of synaptic activity, preserves balance. Dreams, vivid yet ephemeral, may accompany this recalibration, mental fireworks marking the brain's renewal. Their EEG studies reveal that after intense learning, slow-wave activity increases locally in the relevant cortical areas, as if those regions demand deeper rest. The brain, it seems, sleeps unevenly, tending to its weary circuits like a gardener to soil. Elsewhere, genetic research uncovers the ancestral roots of these rhythms. Comparative genomics suggests that sleep-related genes predate vertebrates, existing in primitive animals 500 million years ago. Jellyfish exhibit cycles of activity and rest, even though they lack brains. Their pulsations slow in darkness. When deprived of rest, they show signs of fatigue. Sleep, then, is older than dreaming, older than thought itself.
a fundamental property of living systems that process information. Dreaming, layered atop it, may have evolved as consciousness did. First, flickers of internal simulation, then full-fledged narratives. In this evolutionary light, the dream is not an anomaly, but the apex of an ancient process, the universe reflecting upon itself through neurons. From evolutionary theory to modern therapy, the chain remains unbroken. In hospitals treating trauma, clinicians harness sleep's mechanisms to heal minds. Veterans plagued by recurring nightmares learn to rewrite their scripts while awake, embedding new endings that later replay in REM. Others use medications that modulate adrenergic signaling, diminishing the intensity of fear without erasing the memory itself. These interventions succeed where talk alone fails, because they align with biology's natural rhythms. Healing occurs not only through words, but through waves, pulses, and dreams. Meanwhile, in the realm of philosophy, new dialogues emerge between neuroscientists and phenomenologists. The latter ask, what is the structure of experience within a dream? How does time flow when the brain is detached from external clocks? Experiments reveal that dream time often matches real time within 10%. A minute of action takes roughly a minute of REM. This correspondence, unexpected and precise, implies that the brain preserves temporal coherence even in fantasy. In this respect, the dream world is not chaos, but alternate order, governed by internal metrics of duration and causality. When you run through an endless corridor or watch a sunset that seems eternal, your brain's chronometer ticks faithfully beneath the illusion. Time in dreams is elastic, yet measurable, subjective, yet constrained. A paradox that fascinates both physics and psychology.
The study of such paradoxes gives rise to new methodologies. Machine learning models trained on terabytes of EEG data can now predict transitions between sleep stages seconds before they occur. Researchers feed these predictions back into devices that adjust temperature, sound, or light to guide sleepers into optimal cycles. For the first time, humanity can sculpt its own nights deliberately, tuning the balance of deep sleep and REM like a conductor adjusting tempo. And still, within those optimized nights, dreams arise unbidden, anarchic, untouched by control. The more we learn to manage sleep, the more dreaming reminds us of freedom's persistence inside the skull. Historians watching this progress trace an elegant arc from superstition to science, from divine interpretation to neural analysis. Yet they also note continuities. Both priest and neuroscientist confront mystery through ritual. The modern ritual is empirical, its altar the laboratory bed, its incense the sterile hum of electronics. But its goal remains transcendence, the glimpse of something beyond comprehension. When the brain dreams of itself, it performs a cosmic recursion, an organism reflecting the universe that created it. Every neuron that fires in REM reenacts the birth of awareness, a miniature Big Bang within the human night. Across generations, the fascination persists. In universities, students studying cognitive neuroscience memorize the classic triad of dream features: vivid imagery, emotional intensity, and bizarre narrative. They learn the metabolic rates of REM, the cholinergic mechanisms, the role of the pontine tegmentum. Yet many confess that what drew them to the field was not data, but wonder. The experience of waking from a dream so profound that the boundary between self and cosmos blurred. Science may quantify, but it also rekindles the awe that religion once held. The sleeping brain becomes a sacred object, not of worship, but of infinite curiosity. In the poetic realm, too, dreams regain their dignity. Writers like Italo Calvino and Haruki Murakami draw upon neuroscience to craft dreamscapes that feel both magical and anatomical. Artists project EEG patterns on walls, transforming invisible thought into color and rhythm. Music composed from recorded brain waves fills galleries with the harmonies of slumber. The collaboration between art and science revives a Renaissance spirit, uniting analysis with imagination. Through these works, the public glimpses what research papers cannot convey: the beauty of the brain's nocturnal art. Meanwhile, the sleep scientists themselves continue their vigil. In one laboratory, researchers track infants whose nights overflow with REM, suggesting that dreaming aids brain development. In another, gerontologists study the decline of REM with age, noting correlations with cognitive decline. Between these extremes, the newborn and the aged, the entire trajectory of life is mirrored in the architecture of sleep. To dream well is to live fully. To lose the ability to dream is to fade not only in memory, but in meaning.
And still questions multiply. Why do some dreams repeat? Why do others vanish before dawn? Why do the blind dream in sound and touch, constructing spatial worlds without sight? Each discovery births 10 more enigmas, each answer a doorway to deeper wonder. The science of dreaming, though centuries old, remains a field of beginnings. Every generation approaches it as if anew, armed with better tools, yet haunted by the same astonishment that within the silence of sleep, the universe creates itself again each night through the fragile architecture of a human brain. The quiet persistence of that astonishment carries us into the deepest reaches of the 21st century, where science and imagination once more converge. In the subterranean corridors of a European neuroscience institute, rows of magnetically shielded chambers
glow faintly with the light of instruments so sensitive they can register the whisper of ions crossing synapses. Within one such chamber lies a volunteer, electrodes tracing her skull like a crown of silver. She drifts into the first stage of sleep, her heartbeat slowing, her breath lengthening, her consciousness dissolving into the phosphorescent haze between waking and oblivion. Outside, on the monitors, researchers watch the slow descent of her brain's rhythms, alpha waves folding into theta, theta into the long rolling delta tides of deep sleep. But when, after an hour, the storm of REM begins, the room changes. The data streams pulse with color. The brain's internal lights flare like auroras. Somewhere behind the curtain of flesh, the volunteer begins to dream. For the scientists, this moment embodies everything their discipline has achieved. They can tell, with mathematical precision, the instant her consciousness fractures and recomposes, the regions that ignite, the neurotransmitters that flood and recede. They can describe the choreography of millions of neurons performing their silent dance. Yet they cannot know what she sees. That invisible theater remains sealed, accessible only to her, as if the brain, though mapped in exquisite detail, still hides a secret dimension. Some researchers call it the hard problem of consciousness. Others call it poetry. Either way, the boundary holds. Even as technology nears omniscience, the dream guards its mystery like an ancient temple behind the gleaming facades of science. Beyond the laboratory walls, the implications spread into every branch of human endeavor. In medicine, sleep analysis becomes a diagnostic art as refined as auscultation once was. Doctors listen not to the heart, but to the electrical murmurs of the sleeping brain, detecting the earliest tremors of disease. In psychology, dream reports become tools for tracking cognitive recovery after trauma. In artificial intelligence, engineers study the sleeping brain to design networks that self-optimize through dreamlike replay, teaching machines to refine their knowledge in silence. The metaphor has come full circle. The artificial now learns by imitation of the biological, dreaming as we dream.
And yet, amid this sophistication, a new humility takes root. For every mystery solved, another appears, like stars beyond the telescope's range. The discovery that glial cells, once thought passive, modulate synaptic pruning during sleep has transformed our understanding of brain maintenance. The realization that cerebrospinal fluid pulses in rhythm with deep waves suggests that even cleaning the brain may be part of sleep's design. Dreams, in this context, seem less ornamental than essential, a surface manifestation of maintenance processes that keep consciousness from collapsing under its own complexity. The dream becomes the narrative face of biology's housekeeping, a story told to disguise the brain's nightly repair. In the social sciences, too,
the dream acquires new relevance. Anthropologists exploring indigenous epistemologies find that many cultures treat dreams not as illusions, but as valid experiences of another layer of reality. Contemporary neuroscience, though couched in different language, echoes this pluralism by acknowledging that the brain's internal simulations shape perception itself. If waking life is partly constructed by prediction and expectation, then dreaming is simply perception freed from constraint. The gulf between myth and measurement narrows. The human impulse to find meaning persists beneath changing vocabularies. As the decades advance, interdisciplinary collaboration flourishes. Theoretical physicists, intrigued by the brain's capacity for self-modeling, apply quantum information theory to neural computation. Philosophers of mind debate whether dream consciousness constitutes a separate ontological state or merely a variation of waking cognition. Artists translate EEG data into symphonies. Architects design spaces inspired by hypnagogic geometry. Dreaming, once confined to the private night, becomes a collective cultural project, an exploration of consciousness as heritage. And still the sleeper lies in her bed. Every sleeper on the planet, from the crowded towers of Shanghai to the tundras of Lapland, from the domed colonies of future Mars missions to the drifting ships in mid-ocean, all joined by the same invisible rhythm. Brain waves rise and fall in planetary synchronization, billions of minds rehearsing existence beneath the same moonlight. This global chorus, though silent, exerts profound effects. Empathy sharpened by the integration of emotional memory. Creativity refreshed, sanity restored. The continuity of civilization depends, in ways rarely acknowledged, on these nightly rehearsals of mind. Were dreaming to vanish, culture itself might erode, its stories drying up like rivers cut from their source. The future promises deeper revelations. Already, closed-loop systems allow stimulation of specific neural clusters during REM, creating controlled distortions in dream narrative. Researchers report inducing color shifts, emotional tone changes, even thematic nudges without awakening the dreamer. The ethical landscape grows complex. Can a person consent to modification of experiences they cannot consciously remember? Could targeted dreams be used to reinforce learning or manipulate desire? Philosophers compare this emerging frontier to the first splitting of the atom. Immense potential, immense responsibility. Humanity stands again before a door it both reveres and fears.
Yet, despite these uncertainties, the drive to know persists. New imaging modalities, using quantum sensors rather than magnetic fields, capture neural signals with unprecedented clarity. In these maps,
Scientists watch how information loops through the hippocampus, thalamus, and cortex, forming transient circuits that vanish at waking. Each loop corresponds to a thread of dream narrative. With enough data, they can reconstruct not the image, but the architecture of imagination, the topology of thought itself. In these shapes, some see the embryonic form of a universal language, consciousness expressed in mathematics. Others caution that meaning cannot be extracted from structure alone, that the essence of dreaming is not geometry, but experience. Between these camps, the dialogue continues, mirroring the old conversation between mystic and scholar, intuition and proof. Even as neuroscience ascends toward abstraction, the personal remains. In hospital wards, children recovering from injury recount dreams of flight. Elders in dementia care drift into reveries where youth returns, memory reborn. For them, dreaming is both refuge and revelation. Nurses notice that those who sleep deeply heal faster, their bodies responding to the silent orchestration of hormones and immune cells synchronized by circadian clocks. Sleep laboratories may chase grand theories, but in these quiet rooms, the truth is intimate. To dream is to heal, to reconnect the scattered fragments of the self. Beyond Earth, astronauts aboard orbital stations describe dreams altered by weightlessness. Without gravity, the body's orientation dissolves. Dreams become fluid, scenes shifting like ink in water. REM duration changes under microgravity, hinting that evolution has tuned dreaming to the pull of the planet. Future explorers journeying to Mars will carry with them experiments designed to monitor how isolation, radiation, and distance reshape the sleeping brain. The dream, it seems, will accompany humanity wherever it goes, the last tether to terrestrial origins, a private homeland amid the void. Meanwhile, historians, looking back, trace the continuity of this entire saga. From the incantations of Mesopotamian priests to the fMRI scans of modern laboratories, they observed that each epoch projects its worldview onto the mystery of sleep. The ancients saw gods, the Renaissance saw humors, the Victorians saw symbols, the 20th century saw neurons. Each was partly right, each partly blind. The truth of dreaming, vast and multifaceted, accommodates them all. It is spiritual and chemical, poetic and electrical, personal and universal. To reduce it to one domain is to miss its nature, for dreaming belongs to the borderlands between all categories. In literature and art, that understanding blossoms anew. Novelists weave neuroscientific detail into mythic narratives. Filmmakers depict REM as luminous landscapes of thought. Poets use the language of synapses and oscillations to describe longing. The vocabulary of the lab becomes the idiom of imagination, just as medieval theology once provided metaphors for love and loss. The science of dreaming thus fertilizes culture, not with data alone, but with new ways to conceive what it means to be conscious.
Within academic halls, new generations of scholars debate whether consciousness might itself be a dream, a self-consistent hallucination maintained by predictive processes even when awake. The idea, radical yet mathematically grounded, reframes perception as continuous dreaming constrained by sensory feedback. Wakefulness becomes merely the dream shared by consensus. Such theories dissolve the boundary between day and night, suggesting that the same generative engine operates always, sometimes tethered to reality, sometimes free. The human story, in this light, is the history of a species learning to dream together. But even as theory ascends into abstraction, the empirical pulse endures. In clinics and bedrooms, ordinary people still awaken startled by visions of falling, flying, meeting lost loved ones. They search online for meanings, join dream-sharing groups, find solace in the universality of experience. No algorithm can yet predict the texture of such moments, the scent of an impossible garden, the voice of the long-dead whispering forgiveness, the vertigo of realizing one is dreaming and deciding to leap into the air. These are the irreducible artifacts of subjectivity, reminders that beneath the graphs and chemicals lies the ineffable core of being. Night after night, the experiment repeats. Humanity lies down beneath its technologies, eyes closing, neural rhythms aligning with the turning of the earth. The great electrical tide of sleep rolls across continents like weather, Asia drifting first into REM as Europe descends into slow-wave silence, then the Americas following hours later. From space, were one able to see the flicker of dreams, the planet would shimmer with pulses of light, a biosphere thinking in unison. Within each pulse, a story unfolds, ephemeral yet vital, carried on the fragile currents of biology. The dream, oldest of human experiences, continues its dialogue with the waking world, guiding memory, emotion, creativity, and the fragile equilibrium of the mind. And as dawn approaches, the sleeper in the lab begins to stir. Her brain's waves slow, the storm of REM subsides, the gate of the thalamus opens to the world's first light. She inhales sharply, eyes blinking against the brightness of morning. Around her, the scientists watch the monitors flatten into the calm patterns of wakefulness. They have captured data, thousands of megabytes of numerical truth, but what she carries within, images of cities that never existed, conversations with ghosts of memory, they can never retrieve. For an instant, she lies still, halfway between two realities, feeling both the weight of her body and the echo of flight. Then she smiles, not knowing why, and whispers that she has dreamed of light flowing through water. The researchers note the time, record the final readings, and power down the instrument. Outside, the first birds call. The long lineage from the Sumerian tablets to the digital epoch continues, unbroken.
illuminated by a mystery older than language and as intimate as thought. The story of dreams, of the sleeping brain, of what science knows so far, remains unfinished, an ever-expanding horizon where biology meets imagination, where the mind, even in rest, reaches beyond itself into the endless night.